Hello and welcome to this video which is all about momentum. We're going to be having a look at what that quantity actually is, how we measure it and how it affects our everyday lives. Momentum is actually quite a difficult quantity to define. Many textbooks tend to skirt the issue by simply telling you how to calculate it and what the units are. But let's spend a little bit of time trying to get a real feel for what that quantity actually means. In everyday life, we tend to use the term momentum to describe something when it's moving and its tendency to want to keep going, or being difficult to stop once it's already moving. And that's a kind of useful starting point, but it's not terribly scientific. Let's just think about this in a little bit more detail. Let's suppose, for example, you are playing sports and maybe you've got a ping pong ball coming towards you in a table tennis match, a tennis ball or a football. All going at different speeds, all balls with different mass. If you were going to be hit by one of those balls, there are two quantities which are quite important to know. First of all, the mass of the ball is going to matter, and also the velocity of the ball. Clearly, knowing those two quantities somehow is going to tell you something important about how much it might hurt if one of those balls were to hit you. So if in fact we were to multiply those two quantities together, mass times velocity, the number we get tells us something important about the movement of that object in relation to how easy it would be to stop, or quite simply how hard it would hurt if it actually hit you. We can see here the equation that enables you to calculate momentum. Mass times velocity. And the units, well, they don't have a named unit of their own. We simply use the individual units. So we take kilograms, meters per second. Okay, so let's start by having a look at the momentum of our sports balls in some typical situations. A ping pong ball has a mass of about 2.7 grams. We need to convert that first of all into kilograms to be in SI units. So we're going to divide by 1,000 to give us 0.0027 kilograms. A typical speed from a professional table tennis player would give the ball a speed of about 22 meters per second. So if we multiply the mass by the velocity, that's 0.0027 multiplied by 22 tells us the ball would have a momentum of 0.059 kilograms meters per second. The other lines of the table, for the tennis ball and the football, are completed as well. As you can see, the momentum of the football is considerably more than of the other two balls. So to be honest, that's the one I wouldn't like to have to be facing in a penalty shootout. It turns out that momentum is a hugely important topic in physics. We have a law which talks about the conservation of momentum, which basically says that when two objects interact, provided there are no external forces acting, the change in momentum of one object will equal the change of momentum in the other, but in the opposite direction. Got two trolleys here, trolley A and trolley B. Trolley A has a spring-loaded plunger. We can put them together and release the plunger from A. Now, Newton's third law tells us what's going to happen. A will press on B, and by the third law, B will press on A. So it's no surprise that the trolleys are going to move apart. But conservation of momentum tells us something a little bit more than this. It will actually tell us something a little bit about the velocities with which the trolleys will move apart. Let's just do it first of all and watch what happens. Now, I mentioned a moment ago about momentum being conserved, about the momentum of the trolleys before we release the plunger being the same as the momentum after we release the plunger. And for children, this might seem rather strange. because before they were released, the carts were clearly at rest, and so the momentum would be zero. Neither of them are moving. So how is it that after we've released the plunger, the momentum is still zero, even though they're both moving quite fast? The answer is that momentum is a vector quantity, and we have to take the direction of the trolleys into consideration. If A moves off that way with a positive momentum, then B moving in the other direction must have a negative momentum. That means we can add both their momentums together and get back to zero, which is what we had before we released the plunger. Okay, so now for another demonstration, and let's see if we can get a little bit more quantitative now. I've got my two red cars. They're identical. Each has a mass of 225 grams. I'm going to start off with one of them stationary and send the other one moving into it. When they collide, some blue tack will make sure that they stick together. I'm going to use two light gates to measure the velocity of the moving car before the collision and then the velocity of the two cars together when they move away after the collision. Now remember that we are expecting the momentum before the collision to be exactly the same as the momentum afterwards. Also, before the collision, we've only got one car on the move, whereas after the collision, we'll have both cars moving together. That's twice the mass. It would be worth at this point pausing with the class and asking them to predict what they think the velocity will be for both cars moving off together. Let's have a look what velocities we recorded. Before the collision, I got a velocity of 0.66 meters per second. And after the collision, I got a velocity of 0.31 meters per second. I would hope that your class would perhaps have predicted that the velocity would halve since the mass has doubled, and that is indeed what we have seen. I think before we get into more quantitative examples, it's important to do simple proportional reasoning examples like this with your class because it helps to develop the concept. Okay, so having done an example which relied simply on proportional reasoning to predict the velocity of the cars after the collision, we're now going to do one that's not got quite as nice a numbers. I'm going to add 100 gram mass to one of the cars. This time, working out the answer just by simple proportions won't be quite so simple. So we'll do exactly the same experiment again, get the velocity readings and see how we handle that mathematically. Okay, so let's have a look at what the velocity was before the collision. The light gate is telling me it was 0.64 meters per second. But rather than having a look at the second light gate, let's use the idea of conservation of momentum to calculate what that second velocity should be. And then we'll have a look and see how close we actually are. Okay, so there's quite a lot going on here, and there's a lot of information for the children to absorb if they are to solve these problems mathematically. This is how I encourage children to set the problems out. We divide the page into half, so that on one side we write down everything we know about the situation before the collision, and on the right hand side everything that we know for after the collision. So before the collision I've got my two cars separated, A and B. B is at rest, velocity 0. Its mass is 325 grams. Car A is moving, and we know from our light gate that it was moving at 0.64 meters per second, and its mass is 225 grams. I can now calculate the momentum of each car. The momentum of A, converting the mass to kilograms first, is 0.225 times 0.64. And that gives me a momentum of 0.144 kilograms meters per second. The momentum of B is easy, that's just 0 because it was at rest. And so the total momentum before the collision is 0.144 plus 0 is 0.144 kilograms meters per second. Now let's look at the situation after the collision. The total mass of the two cars is 550 grams. We don't know at this stage the velocity because we're going to use conservation momentum to try and calculate that. So we're just going to call it V for now. So the momentum after the collision, treating both cars now as one object, will be 0.55 multiplied by V. So the total momentum will be 0.55 V. Moving to the bottom of the page then, we can put these two pieces of information together. And I always think it's important to start off with the statement of the law. So we write out that the total momentum before the collision equals the total momentum after the collision. Putting in the numbers before the collision, I had a total momentum of 0.144, and after the collision we have 0.55 V. I can rearrange to make V the subject of this equation and simply divide to get an answer for the final velocity. And that comes to 0.26 meters per second. It's always quite a magical moment for the children when you can actually get the mathematics to predict a correct answer from the actual experiment. So now let's have a look at the final light gate and see what answer we get. And the final light gate is reading 0.25 meters per second. That's pretty close to the calculated answer. Conservation of momentum applies in explosive situations as well. Let's have a look at this one. I've got here simple trolley on casters set up as a catapult and 100 gram mass loaded into the catapult there. We're going to release the catapult by burning through the string. And again, a bit like the two trolleys we started with, Newton's third law suggests that they are both going to move off in opposite directions. Are we actually going to be able to measure the velocity of these two things as well and check the conservation of momentum? Let's have a go. Well, not surprising there, they moved off in opposite directions, and the trolley, having more mass than our weight there, didn't move off with quite as much velocity as the mass. Okay, well now all that happened just a little bit too fast for our usual light gates. But what you can do if you want to analyse a situation like this, which is quite a fun experiment to do, is you can film it on a phone camera in slow motion. You can then use free downloadable video analysis software to analyse the motion of both the trolley and the mass as you filmed in slow motion. Let's have a look at the slow motion version of this. Okay, so I've taken my slow motion footage and I've downloaded it and put it into the video analysis software. On the screen you can see the displacement time graphs for both the trolley and the mass. I've calculated the velocity of each from the gradient of the displacement time graph. It's important to point out at this stage that because we were using slow motion video, the velocity that I've calculated has been slowed down. And so I can either scale my answer up by the same factor that the phone slowed the motion down, or I can simply keep it in arbitrary units, which is what I will do, because all I'm trying to prove here is that the momentum of the trolley was equal and opposite to the momentum of the mass. So I just need numbers of comparable size, even if the units are now not in SI. So looking at the top graph, which is the displacement time graph for the trolley, I'm getting a velocity of minus 0.062 units. Its mass is 363 grams, and so multiplying those two numbers together gives me a momentum of minus 22.5 in arbitrary units. The bottom graph is the displacement time graph for the mass, and in the video the mass that I used was 74 grams rather than the 100 gram mass I used a moment ago. The gradient tells me that the velocity was 0.32 units, the mass of 74 grams, so it gives me a momentum of 23.7 arbitrary units. Conservation momentum tells us that the momentum of each item there should be equal but opposite. So we've got minus 22.5 for one and plus 23.7 for the other. I think, considering how difficult it is to actually measure such an explosive situation as that, those numbers have come out pretty much the same. We've talked a lot about conservation of momentum and how it applies to Newton's third law, but it also applies in the case of Newton's second law as well. It helps to develop the second law to give it a slightly wider definition. Let's take a closer look. Starting with the second law equation, we have force equals mass times acceleration, or F equals ma. Now earlier children should have learned that acceleration is the change in velocity over the time taken, or acceleration is v minus u over t, where v is the final velocity and u is the initial. If we substitute this expression into the Newton's second law equation, we'll get F is equal to m v minus u over t. Now, another way of writing the change in velocity is to write it with the capital letter delta, which means change of. So instead of v minus u, we can write delta v, and instead of the time taken, we can write delta t. If we look just at what's on the top line, the mass times the change of velocity will actually give us the change of momentum. So that m, delta v over delta t, is the rate of change of momentum. So now, instead of talking about Newton's second law simply in terms of acceleration, we can rewrite the second law by describing the force as being equal to the rate at which the momentum is changing. So this new way of thinking about Newton's second law has got lots of applications in everyday life. We've just said that the force is equal to the rate at which the momentum is changing. And so if we can make the momentum of an object change more slowly, the forces will be less. For example, in modern cars, the front of the car is designed to crumple and collapse if there is a collision, whereas driver and passenger are in a more rigid safety cage. As the front of the car collapses with its crumple zone, the momentum of the car is changed over a greater period of time, which means the energy can be absorbed in the collision and the forces are a lot less. Okay, so the same bit of physics applies to any situation where we have a soft surface which will allow the momentum to change more slowly and therefore reduce the forces. Some obvious examples would include the surface of children's playgrounds and gymnasium crash mats and even cycle helmets. Hope you found this video useful and thank you for watching.